Let's wait for. Am I audible? Hello.
Yes.
Okay. Thank you. So let's wait for 2 more minutes and then we shall start with this week's discussion. So, so let's begin with the overview of the last class and last 5 lectures of the week. That's week 4. So mainly this week mainly focused on the wide area monitoring technique and the architecture of how these wide area monitoring system works in the smart grid, in the modern smart grid, and mainly the various aspects that are being discussed, are all of these that have been shown here. But before that, what is the need of wide area monitoring? That's main question. That suddenly why did we require, means why, what was the requirement to shift to this wide area monitoring system part? So basically, uh, when the entire power network, the entire grid that has to be monitored is quite uh, quite vast in the nature. So mainly we need to find out the proper monitoring states of the system so that we can perform each and every aspect, like the optimal power flow, economic dispatch, all these things, load forecasting. So everything needs to be addressed, and for that we need to have the proper visualization of the entire grid, which is mainly the transmission in most of the cases. Here the discussion will be mainly restricted to the transmission and also the distribution side, because the smart grid architecture mainly uh, focuses on the renewable, how the renewable integration can be merged in the normal operating with along with the transmission side. So what advantage does this wide area monitoring system gives is that, yes, so mainly the wide area monitoring system gives uses the global positioning system. So it mainly use the GPS. The WAMS technology mainly incorporates the global positioning system, that GPS, and with the help of this global positioning system, we can measure the magnitudes as well as the phase angles. So what does this magnitude and phase angle? adds advantage to the normal operating condition is that before we had the RTU based, or rather the SCADA based monitoring system, which was quite present the scenario also. This is quite in use, but the thing is that the SCADA measurements are mainly restricted to the voltage magnitude measurements, power real power injection measurements, reactive power injections, power flows, real power flows, and reactive power flows. So mainly this measurement was restricted to the magnitude portion. So, and also the current flow magnitude, the current flow magnitudes. So the problem issue was that we need to find the base operating magnitudes and volt and the phase angles of all the buses, so that we have the entire picture of how the entire power system or the grid is operating. So base states are the magnitudes and the phase angles. So these are the base base states. So mainly we are looking to find out the magnitude and phase angles of the entire power system in operation. So what advantage is that, what advantage it gives, the PMUs give, means that is the use of this wide area monitoring system gives, is that it directly allows us to measure the magnitudes and phase angles of the system. And these are the and base states of the system. These two are the base states of the system. So for real-time operation, so suppose for the real-time monitoring system, real-time monitoring, our major aim is to find out the all the bus voltage magnitudes and their corresponding phase angles, and this comprises of the state vector. And based on the state vector, everything now we can reconstruct, means the if we are if there is a need to find out the power injections, then we can find it out from this vi vj yij vij cos theta ij minus del I plus del j. So this would give the bus power injection, real part of the bus power injection. For all these things, the admittance matrix is known to us. This admittance matrix, sorry, this is not matrix. The entire admittance matrix is known to us. So based on the admittance matrix, so all the line parameters are known. So in any case, we can always construct the admittance matrix. Line parameters known. So based on that, Yij, this portion is always available. Their corresponding theta, the network configuration topology, it is known to us. So theta Ij is also known to us. So what is known from the WAMS technique or the phasor measurement unit is that we have the direct measurement of the magnitudes and their phase angles. So what we can do is that we can directly put these values here and reconstruct what is the real power flows or reverse bus power injections in the system. So this gives the added advantage over the existing RTU technique. So using the RTU techniques, what in this case also, what we need to find out is the to find out the base states, we need to perform the state estimation. The state estimation is state estimation we in state estimation we consider large number of measurement sets, large measurement set vectors, at least to make the system observable means the measurement size of the measurements should be greater than the number of states, and it is kept around 1.7 times in general case 1.6 to 1.7, sorry, 1.6. So this is the in general the measurement redundancy, that is the there should be more number of measurements than the states. So what in RTUs, for the RTUs what we need to perform is that since then the monitoring system is a real time application of the power system, it is performed in real time basis, on real time basis. So for that we need to construct all the measurement vectors are required to be constructed. The measurement vectors, suppose the power injections, or suppose the bus power injections. So this forms the nonlinear measurement vector. For if we use the RTUs, then we are getting P injection as the measurements. We are getting the P injection as the measurement, but we from the RTUs we need to reconstruct and find out the state vectors. So this is a nonlinear technique that is generally performed, and by using these measurements directly we can reconstruct the states of the system. And the RTUs also have the errors, the metering errors in them. So these metering errors are considered to be for power injections 1%, or the voltage magnitude is considered for power injections it's 1% approximately, and for the power flows it is around, also it is considered to be 2% or something. But so what advantage is given by the PMUs is that they can directly give the phase magnitude and the phase angles, and these are the base operating states. And the accuracy of the PMUs are also quite high, means they are around 0.1%, 0.01% errors inbuilt in them. So they give the so so this is the advantage, that is the we have the yes. So for this purpose, the wide area monitoring system gives the advantage over the RTU based, the SCADA based system with higher accuracy, as well as the direct linear combination of the magnitudes and of the measurements with the states. And hence this technique is recommended for the future EMS system. But the problem is that the cost of these techniques or technologies are quite high, and hence uh, this can't be directly implemented in the present scenario. And what is needed to be performed is that the an existing architecture has to be collaborated with the upcoming architecture of the, means that is the WAMS based architecture, where the entire the SCADA based system as well as the WAMS based system, they they should interact, and for that purposes some means research is going on to how to make these non-communicable systems much more communicable, or rather whatever measurements or the measurements that can be fed by the worms based, or rather what is required by this worms based technique, they can be fed by the previous SCADA based architecture to aid the measurements, and hence to perform the better, this means perform the to make the outcome in a better, in a much better approach, because we can't replace the entire system in one go. So that's the main issue, main challenge. So hence this is the main objective. So coming back to the, so these are the WANs based monitoring aspects. So monitoring aspect I have discussed that it gives the monitoring advantage, as well as the post disturbance analysis, that is after the fault has occurred. So since we have a large number of measurement data, means the refresh rate of the sampling rate is quite high, and with the sampling rate it can be directly kept into, means with these high sampling rates, suppose for 50 samples per second, 50 samples per second is quite high, and hence we can find out the exact what issues went through while the operation was on or anything, or the switching, some switching takes place. Then we can find out the various kinds of effects like the transients effects. And so now this one is the adaptive protection part. Adaptive protection part is that with the protection, the measurements are required to, for in the protection objective, on the protection perspective also. So what is the advantage given is that in adaptive protection, the main aim is that the protection scheme should work in based on the various kind of means, suppose we have a system, suppose we have a system. So here the parameters of the systems are changing based on the real time operating scenario, so which is quite obvious in our present day distribution system or the smart grid technique. So this adaptive protection, on the basis of that, the relays should coordinate in such a fashion so that the adaptive scheme should be maintained, because if suppose the relays are set to some particular value, and based on these variations in the system parameters, the now the system set value should be changed, or rather it gets changed to some other points. So the protection scheme should be adaptive enough to consider all these changes and deliver the results as per the requirements. And the restoration activities, so if we have these huge amount of data, or if we can visualize the entire scenario, then the restoration activities would be easier, because it would be, means to pinpoint the fault location, or to pinpoint the other, means the disturbance location, it would be quite easier, and hence the what measures should be taken, that the operators would be having a clear picture of what measures should be taken, and where the action should be done, so as to fast so as to means to execute faster restoration activities. And the controllability, it's a smarter control of this system. So here we can see that the data that SCADA connects data in 1 to 2 seconds. So 1 to 2 seconds in general case, it's written 1 to 2 seconds, but in present day scenario, or in the research papers also, it is generally considered uh, to work in 2 to 5 seconds, or 2 to 4 seconds. So, and that too also in not in synchronism, means asynchronous. That too also in asynchronous mode of operation, means the time stamping, there is no fixed time stamping. The time stamping is done by the server and not by the measuring device itself, in the device. So there are some issues related to, whereas the WAMs collect the data to 20 to 60 times per second, and hence the in some cases also post-mortem analysis is done, means in the 2012 blackout, to restore the means after the during the fault, during the overloading scenario, when the distance relay is uh, tripped off and due to the line overloading limit, and hence there was a cascading effect, and hence the entire western grid and sorry, eastern northeastern grid and northern north grid, all these three grids were first in the western grid also. Western grids, all these four grids were affected, and hence the main issue or the main challenge is that when the postmortem analysis was done, so it was came to the knowledge of the operators that it came to the knowledge of the operators that they window of uh, only had a window of uh, 3 seconds to necessitate the proper action. So this can be done only with the help of means smarter smarter operation schemes, means the it's rather impossible for a personnel to react to some this kind of contingent situation uh, in such a faster time frame. So what we can see is that WAMS enriches the real-time monitoring of the system, right? So this is the WAMS structure where we can see that there are the PMUs being located at various locations. Here we can see PMU, all the transmission, all the substations are being given the PMU. Here in the distribution side, we have the micro PMU, where the micro PMUs do have the higher refresh rates. It's generally in the range of 100 samples per second, 100 samples per second. So all these feeder terminal units, FTUs, mainly the WAMS based technique means we will have the micro PMUs, the PMUs, and they would be communicating to the PDCs, or rather to the PDCs, and the PDCs would be communicating to the super PDCs. Okay, so here we have the control center, but we have the control center, and this would give the operators or the personnel sitting there uh, to have a close overview of the and also the faster overview means for this database system, when where we have the data rate from 2 to 5 seconds, and here we have 50 data in 1 second, 50 samples per second. So here the monitoring would be easier, and also the accuracy of these devices are faster, and also these devices are synchronized. Synchronized means the PMU here would be giving the data at the same timestamp as the PMU here, and also there. I mean, it's all throughout India if we consider the Indian grid, and also these micro PMUs. Considering the micro PMUs, every PMUs or micro PMUs would be delivering the data on the basis of on a synchronized fashion, and that data would be time stamped on the meter itself, and hence that they would be giving much beneficial impact on the monitoring aspect, and how the grid would be now on the basis of these. Some real-time market scenarios are also getting established, real-time market analysis are being done, the load forecasting. For the load forecasting part, we require large amount of data. So since we have the large amount of data from each and every devices on a granular scale, so we can easily find out the proper, or rather find out the proper load forecasts of the, rather also in general cases, these micro PMUs and all these things are not being placed in a much higher scale, or rather in a greater scale in Indian context. IIT Bombay was working on the PMUs, placement of PMUs, around 1500 PMUs in 600 in PMUs in 600 uh, buses, 600 buses which are more than 400 kV, and 100 buses which are more than 700 kV. So this a total 700 buses are being monitored on the basis of the optimal BMU placements, and this work I think is over by now. IIT Bombay was working on this project. So microgrid monitoring on the distribution scale monitoring. So if we can have this kind of higher flexibility on how the load forecasted load would be, or the forecasted load would be obtained, then so on the basis of real time data, then that would be a prior advantage to the previous normal architecture, means SCADA based architecture. So these are the positive notes on positive side. So energy management system, this is the energy management system part, where we have the pre-dispatch function where load forecasting needs to be done, scheduling needs to be done, unit commitment needs to be done. So outage planning. So main aim of the load forecasting, when we perform the load flow analysis in our system load flow analysis. So we have three kinds of buses, right? PV buses, PQ, PV buses, PQ buses, and the slack bus, not buses. So here the generators for the PV buses, the generators are connected. Generally, generators should be there for the or the voltage support. It should be there. And for the PQ buses, we have these are mainly the load buses, and these are the slack buses. So one thing I would like to point out is that for the PV buses, so these PV buses, this P. So can anybody tell from where does this P come from? P value before performing the load flow analysis, we take use of take we consider this P value, this V value. From where does this P value come from, or V value comes from? Can anybody for the PQ buses? Where does this P comes from and the Q comes from? Any guesses?
For PV buses, P comes from the installed capacity of the generator, and V is also the, the voltage of a bus. That means from where transmission takes place from the generator.
Yes, but means what prior means there are some this forecasting, all these things are previously performed to obtain these P and V values of these which are taken, means these P V P Q values are considered for the load flow analysis. But prior to the load flow analysis, we need to find the value of, let us consider it as a PG, means generator bus, and this as a VG, because this V and K. So so this PG comes from this PG comes from the um, load dispatch unit commitment. So these exercises are first performed to find out what would be the PG values, which generators should be invested for the next 15 hours slab. So the day ahead market or the day ahead forecasting. So in the day ahead forecasting, for 15 minutes, entire 15 minutes time slabs, the all throughout India, the generators are scheduled. So from where when these schedules are performed, means for suppose for today, if we perform this scheduling today, it has to be used tomorrow. Means for tomorrow we will be performing this optim this scheduling, this PB, PG, and all these values we would be finding out based on for every 15 minutes slab, because every 15 minutes it's considered the loads do change, although it's considered as a quasi static in nature, but after means it is a general consideration that for 15 minutes slab the loads do change. So this PG is obtained from this economic load dispatch sheet exercise, unit commitment exercise. For 15 minutes slab, suppose their load has to be made 400, sorry, not 400, it's quite high. So suppose 200 gigawatt load has to be made all throughout India. So which generators should be placed into action? What are the renewables that would be coming into place? What would be the solar forecast and all these things? And based on that, what would be the thermal generator schedule, or the unit committed units, what which unit should be committed? So this we need to perform first to obtain the PG value. Now coming to the this P part and this Q part, this load P, the for the load bus P, it is generally performed using the load forecasting exercise. Based on the load forecasting exercise, this PG value, P load value is obtained. Let's consider PL, QL, and this QL is performed based on the active power loss minimization. Active power loss minimization. And this VG, let me call this VG, is generally performed. Uh, okay, this VG voltage. VQ. Okay, let me rethink VG part, and I will be telling VG. Okay. So these are the prior exercises that are performed means before the for the next day's entire load scheduling. So
Sir, what does this slack bus do?
the slack bus, the main objective of slack bus is to deliver the real time means the present in the present scenario. The slack bus, here the known parameters are V and delta, right? So if we have the knowledge of V and delta, then what are the unknowns for the slack bus? The unknowns are P and Q. The unknowns are P and Q. So it is taken into consideration that the slack bus would be delivering the resultant amount of power. Means the suppose we have a load P D is the demand and PG is the generation by all the other generator buses. So suppose this, if we don't consider the slack bus, so only PG, if we consider the PG which is delivered by the other generator buses or the generators rather. So if we take into consideration that the PG is lesser than P demand, then the remaining amount of the load or remaining amount of the demand that would be delivered by the slack bus. And it is quite a conventional approach, but in practice it is not performed. In practice means it is there are some assumptions that at least the would be slack bus would be having it would be the largest bus among the all largest generator among all the generators, and also it would be having infinite voltage support and all these things, but in practical case that doesn't offer. So for that it is generally performed that the participation factor based load flow is performed, where the all the generators do share the losses as well as the remaining loads which can't be generated. Means if we consider only the case of slack bus, it is the main purpose of slack bus is to deliver the remaining or the resultant loads as well as the losses or the system losses, line losses and all these things in the system. So that's why this P and Q are kept unknown. Means these entire value that can't be delivered by the other buses or sorry other generator buses or other generators, that would be delivered by the slack bus.
So can we say now that storage, battery storage, and all the storage capacity what we have discussed can be connected to Slack bus?
Yes, it can be connected, but the storage batteries are itself as considered to be the generator buses. Okay, because they are delivering loads, so they are generator buses. So what I have told is that presently the participation factor based load flow is performed. So here in the participation factor based load flow, all the generators should take up the losses and should take up the losses in their proportionate manner. Means suppose if if we consider the batteries which should be in Indian scenario, it would be in in kind of not in multiple, means a fractional part of that of the uh, generators, most of the high end generators. So if it can be it would be delivering as per proportionate manner, it would be delivering the loads, delivering the losses. So we can consider, we should convince, it is considered the batteries that are connected are considered as the generator buses. If they violate the voltage support limit, means the voltage, the reactive power limit, because all the PV buses we have the reactive power limitations. If this reactive power limit gets violated, then it would be considered as a PQ bus for the upcoming iterations. And later on, if again each and every iteration the reactive power limit violation or limit check is performed, and based on that we can switch between PV PQ based on how whether the limit within limit or violated. So yes, batteries will be considered as the PV buses in present load dispatching problem. All the wind power plants, the solar power
But
plants.
but sir, our concept of storage is not a continuous. Whenever it
Yes.
is required, it will be switched on. So why
Hmm.
we are not considering battery as a what you say storage, whatever storage capacity we have learned in
Hmm.
a Slack bus?
So we can't consider in a slack bus perspective. It has to cater the system losses in a participative manner. In present participative manner, the battery storage devices don't have that much capability to generate or to deliver. It means it's generally taken into consideration that the higher higher rated buses, higher rated generators would be considered as slack buses, which has the ability to deliver the loads, means losses on a higher scale. Means but if we consider the battery energy storage devices, so these battery energy storage devices, uh, I don't have the view that whether these battery energy storage devices do have the capability to be considered as slack bus, because they are quite limited. Means their generating capability or is quite limited in the present day scenario. So uh, there are some limitations. So in this load flow aspect, the it can be considered, but then it has to deliver the or meet the demand as per the requirement of the, means there will be some changes in the system. So it has to take up or cope up with the changes of the system. Although the battery energy storage devices, uh, they have this kind of they don't have the increment or decrement. Means we can't increase, suppose there is a definite load demand, sudden rise in the load demand or sudden fall in the load demand. So this kind of objective, means this kind of, since it is a static device, so they don't have that much that capability to deliver the this kind of issues, means this kind of scenarios where the load changes occurs and all these things. So that can be a case, sir. So, Hello. Hello. Okay. I think yes. Okay. Then- So, as a part of the energy management system, so these are pre-dispatch functions. Then we have the real-time operations, where we first need to perform the state estimation, and this state estimation allows the entire or the operators to have a clear picture of the working states of the system, that is the all bus voltage magnitudes and their phase angles, and based on that contingency analysis, security assessment are being performed. Real-time generation control, automatic generation control, scheduling control part, worldwide dispatch, these are done. And post dispatch activities which can be done are mainly the data recording, historical management, sequence of event, load flow studies. So these are mainly the energy management system, main purpose of this energy management system, right? So these are the PMU benefits. So it would be giving the wide area situational awareness for the operators for improved visibility. So what I've discussed is that this would be aiding the improve, means the visibility of the entire operation would be improved, or by the from the operator's perspective they would be having granular data, and based on that they can means automatic monitoring would be a better alternative, but based on the data, means the granular data, they can have the idea or the image of the exact operating conditions of the system. Determine the stress points, so the lines are overloading limit of the lines are violated or not. So in PMUs also we have, they have the facility of measuring voltage magnitude, phase angles, frequency, rope of rate of change of frequency, and also for the current part, so real part of the current and imaginary part of the current, imaginary part of the line current flows, this can also be measured. So what this real and imaginary part of the line currents can be reconstructed to the current magnitude and phase angles. The main necessity of using this real and imaginary part is that for the real-time analysis, like the state estimation, which is a real-time monitoring aspect. So in WLS, weighted least square based estimating technique, what we need to do is that we need to invert the Jacobian. So as we all know that inversion of Jacobian the inversion is the in the supercomputing architecture, it is not that much a problem, but considering the previous power system scenario, inversion was the most time consuming and memory consuming activity that was to be performed. So what the people in the when they developed these PMUs, they came with the with the research is that if we consider the real and imaginary part of the current, because in the estimation aspect we need to convert the measurements into their nonlinear function form as a representation of the state vectors. So what we can do is that if we measure the currents in this form, the jacobian the jacobian the area, means the convexity of the Jacobian. If we perform this inversion, then what we observe is that the if we consider the real and imaginary part, this would be a 3D kind of figure. Means how to draw, I can't. That this would be a 3D kind of figure. There are research papers where the people have demonstrated that if we consider the line measurements as magnitude and angle directly, then the Jacobian there is a shift in the scale, means from the zero, this is the zero, this is the three-dimensional scale we need to consider. So what we can observe is that it comes down with the kind of this kind of, means I can't draw it here. So that's the reason. But if we consider for the real and imaginary part, the Jacobian section remains positive all throughout, and hence the inversion process is easier, and hence the state estimation can be directly implemented. So that's the usage. What that's aided the use of real and imaginary part of the current, where we from where we can directly reconstruct the magnitude and angle part again. Okay, and also instantaneous measurements and early warning detection alerts from the SCADA system if it gets missed, and system-wide PMRF future implementation, big data analytics for future data analytics, post-mortem analysis, where the post-mortem analysis, machine learning techniques, where the data we can perform the data-driven approach, where the people can directly detect the means the topology of the system. Since the topology is varying in nature, so we can do is what we can do is that directly based on the data, the system that the architecture means, suppose we can consider the suppose ANN, the ANN architecture, artificial neural network based, so they can directly frame the operating or the system model, and based on that they can deliver the result. If they have a large amount of data, the system training and testing validation procedure gets easier, and hence improve the power system to prevent outages. So this was the section which I was telling, that if we consider the same system to be monitored by SCADA and PMU in the graph in this diagram, what we can observe is that if this the same system is being monitored by the PMUs and SCADA, so these transients or these sudden changes, they can't be captured by the SCADA based system, because SCADA communicates on a basis of 2 to 5 seconds, and based on 2 to 5 seconds, that too also in an asynchronous fashion, they do communicate. And so the entire dynamic behavior can't be captured with the help of the SCADA. So there it has some disadvantage, and the PMUs, as we can observe, it can capture the entire dynamic variations, and these dynamic variations can be used in various kind of dynamic of the generator parameter state monitoring of the system, and based on that the controller action can be devised, means the separate controller action can be made based on the data driven approach, or we can perform the various kind of control, or the suppose we can also perform this parameter estimation, or parameter find out the parameter estimation based on these metering devices or the measurements. Okay, so this granular architecture, granular data processing aids in delivering better outcomes, as also the accuracy of these devices are also quite high. So applications coming from the applications, so transmission system monitoring, already I've discussed that transmission system monitoring, how the PMUs aid in transmission system monitoring. Then distribution system monitoring. In the smart grid architecture, the distribution system monitoring is a prime objective, where we have the micro PMUs placed in the system. And generally, distribution system is considered to be radial in nature, but considering the present day scenario, uh, the loads are generally mainly it is radial, but presently weekly meshed weekly mesh topologies are being formed because of the DER penetration. Suppose we have a DER here, and this DER is also feeding. We have a DER, and this bus is also feeding some other buses like this one. So we have the weakly meshed, not mostly the architecture would be less meshed, because they as we make this system or structure towards the mesh architecture, then the protection device or the protection cost of the equipment would also increase. So to make these things simpler, mainly it is considered to be uh, weakly meshed system, or rather it is weakly meshed system. So distribution system monitoring, what we generally do is that in the substation, this is the substation or substation bus, the substation. So here mainly we have we place a micro PMU, and if we can place a micro PMU in all the buses, that's a drastic scenario that we can't do in a present, and we can't think of in Indian context. But that would make the distribution system quite comparable to the existing transmission system. That can't be done, but yes, people are trying to do so that the so it's to monitor the distribution system in a much better fashion, because mostly we have the bidirectional power flow here also in the distribution based on the smart grid architecture, a modern architecture. So just that's the main agenda. And here we have the DER monitoring. So if we have a huge amount of data, means we can monitor the systems in a much better fashion. Although in the distribution system we don't even have that much access to the smart or access to the real time data, because uh, it is impossible to actually it is impossible to place these RTUs at each and every node, because there are huge number of nodes in them, right? So if we have such a large number of nodes, so it's quite impossible. So what people generally do is that if we have a transformer here, and this is the LV side of the system, up to this is the MV by LV side, this is the 400 kV. So people generally do is that, and we need to have a quite number of measurements to monitor the system properly. So based on the so to aid that scenario, we have this LV site. This LV site have the consumers as the means that we have the customers, that is household premises. So household customers do have these present scenario, they have the access to the smart meters. So based on the smart meters, now in Indian context, the government, as per government rule, each and every house, if we can directly monitor the smart meter, then the main problem is that the theft issue. That if we can consider, if we can always find out the people who are there in the room based on the power consumption profile, if these smart meters are directly communicating to the DSO, as because DSO model has been proposed in recent time. So since these smart meters, if the all these smart meters do communicate with the DSO, distribution system operation or control room, then the issue would be that the people sitting there would be having the clear view of the people who are there inside, people who are there inside the room or not. So okay, let me check whether recording. Okay. So they won't be having this view that the people who are residing inside or not. So based on this means if the DSOP operator, means the distribution system operators, do start communicating with the or giving this information to the various would be leading to some theft activities from the room, because they would be having the clear picture who is inside the room or not based on the power profile. So what government has allowed is that they can take this LV side, suppose in this MV side also, in the MV side also, we have large number of, from the MV side there are large number of LV nodes. So based on the LV nodes, what people can do, what the DSOs can do is that they can take the aggregated smart meter data, they can take the aggregated power profile, aggregated power profile of the entire of the nodes, all the nodes which are downstream to that of the MVLV node. And this MVLV node, this MVLV node, this measurement, aggregated measurement in the MVLV node would be considered as a measurement for the real-time monitoring of this entire distribution system. So these are the challenges now, because people can't place the directly these metering equipments, or rather they can't communicate. Make the entire first challenge is that people, the distribution system operators can't directly place these micro PMUs on a large scale basis because it's too costly, and in the Indian context, the RTUs are also not up to the mark. Means they are placed, but not up to the mark what that should have been placed. So people do use of these aggregated smart meter data at the MBLB level, and wherever there is the deficiency of this smart meter data, then people do choose the DSOs, choose the, or rather, not, let's not consider DSO, because the prospect is the objective of these DSO planning and all these things have been recently proposed some 2 to 3 months early only ago. So that can't be a case in Indian context, but in others, in outside India, this smart grid architecture based on this distribution system side monitoring can be considered as a this this smart meters would be delivering data, aggregated data, and the nodes where we don't have data, we generally take use of the pseudo measurements. And what are these pseudo measurements? These pseudo measurements are the based on the historical data of that node. Means suppose people do have the load forecasts of the system, they do have the load forecast, and based on the load forecast, what they can perform is that they can find out the future forecast, means future operating, or rather based on the forecasted load profile. Suppose day before yesterday that was some value was there during this time, and all throughout the year, if suppose from 4 to 5, or rather 4 to 4:30, if this was the load profile, then that can be constructed to a futuristic load profile, which can be used as a measurement for a real time monitoring of the distribution system, right? So this is generally done in distribution system. So this is from the slide itself, where the resolution 2 to 4 seconds, 10 to 60 samples, where PMU's advantage, magnitude and phase angle, that I have also discussed. The time synchronization, no, it is yes, right? Here analog 100 plus analog, and here we have these 10 phasers, 16 digital and analog channels. So 16 plus mainly. And this is local monitoring, this is wide area monitoring. So if we can make wide area monitoring, then the communication between each and every place would take place, and hence that would aid in the proper working of the smart grid architecture, because data communication, the communication layer in IT layer and the OT layer, means the operation layer, all these three things would makes up this smart grid. So this is the main aim, is to have a entire usability of these three things, means the operations, communication, and in IT means the information technology. So these things can be delivered by the PMUs. So here we have these PMU located at the substations, and the PMUs are located here. And based on that, we have the data concentrators, hazard data PDCs, hazard data concentrator, and then we have the super data concentrator. This is the working model of the PMUs, how the data gets transferred, and these optical fibers that are, means what we can see is that in the transmission line OPGW, the optical fibers, ground wire, means the top of the towers we have the ground wire. So in the inner side of the ground layer, ground wire, outer side is ground wire, but in the inner side it is optical fiber, and the information gets communicated to the, in Indian context, if we consider, from the ASL, from the, means the ALDC is area load dispatch center, to the SLDC, to the RLDC, and then to the NLDCs. And the NLDCs would be mainly dealing with the measurements, and then they would be delivering some outcomes, and again to RLDC, to SLDC, and then to ALDC. So this is the main architecture, and PMUs, how the PMU starts communicating. So if suppose the phasor data concentrator sends the command frame to start data, then the PMUs start the data means the, so PDCs would be giving the command frame means the start command, and based on that the data would be transferred, and after that when the PDCs would be giving the command frame for stop data, then the PMUs won't be communicating again till the next command. Okay. So this is the mainly the architecture where how a PDC or PMUs do work. So as yes, so this is the optimal PMU placement example. This I have referred from this paper, highly cited paper. This one. So it is in the present day context, optimal PMU placement is quite important because the people can't make use of this means the IIT Bombay project also it was mainly of the optimal PMU placement because the optimal PMU placement would aid in proper means the system should be observable since the PMUs if we have the PMU placed at this bus then if we know the line parameters and we generally know the line parameters of this if the end of this network then if we have a PMU here then using and we know the voltage magnitude and phase angle at this bus, so using that voltage magnitude and phase angle we can find out the voltage magnitude and phase angle of this bus given the fact that we know the line parameters. So so this makes the system observable means by placing a single PMU here we can we can have the information of two buses means one for this one and the other by using the line parameters we can find out the drop of the system and hence find the line voltage and bus voltage of bus number. Suppose this is bus number 1. Suppose this is bus number 1 and this is bus number 2, so we can have the information of bus number 2 by only having PMU placed at bus number 1. So this is the usability of the optimal PMU placement. If suppose the IEEE the here the another thing is that zero injection buses. So what are zero injection buses? ZIBs. Zero injection buses are those buses where the net power injection is zero. So what advantage does it give is that these zero injection buses can be treated as perfect measurements for these problems. Perfect measurements and with no standard deviation means zero with or rather very small standard deviation means it's generally considered to be zero or nearing to 0% standard deviation, so this can be considered as perfect measurements. So in optimal PMU placement what we can observe in IEEE 30 bus system, and these are the test system in which people need to develop the system model and they can test on these because these data are being given in the IEEE website itself where it is open source. People can get access of this data and they can test their objective or their simulation or the simulation study before applying in the practical scenario. So what it is observed that in the normal operating scenario without the zero injection buses, so let's consider they haven't considered firstly it didn't consider the zero injection buses. So in such a scenario, what we can observe is that we require 10 PMUs are required to make the system completely observable. Means there are 30 buses observable by only 10 PMUs. Means if we have only 10 PMUs, then the entire information of all the buses would be available to the monitoring or the control room. So, and using the zero injection as the equality constraints, then what we can do is that what we observed is that the number of buses required, number of PMUs required are less because these measurements that are being given considered as zero injections are of perfect measurements, are mainly perfect measurements. So, the number of PMUs required are 7 here. In this case, it's 7. So Only using the 7 PMUs, the entire system of 30 buses are observable. So this is the main usability of optimally placing the PMUs. And suppose if outages are being considered, then the PMUs required would be higher. Although the entire all these buses won't be requirements, all the buses is based on their connections or the topology. Then based on the topology means this PMU placement can be considered. Means that the result or the outcome of this optimization problem would be based on the system topology, because if suppose an outage occurs in a bus in a bus which is connecting to the large number of buses. So if outage occurs in such a position, then the branch outage, if such a branch outage occurs, then this kind of placement of higher number of PMUs would take place. Although the PMU placement number of PMUs placed at the buses are lesser than the number of buses. Okay, and considering the zero injection cases, this would result in much lesser PMU placement. And this is for the IEEE 30 bus system. You can go through this paper. Uh, suppose this is the test system. This is a New England 39 bus test system. So here also the authors have performed this test on the new normal operating case. The normal operating case and the single branch outages. So here we can observe is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So using these 13 buses, the entire system of 39 buses becomes observable if we don't consider the zero injection buses. And if we consider the zero injection buses, then the number of PMU placements would be much lesser. That is 1, 2, 3, 4, 5, 8. Only using 8 PMUs, the entire system becomes observable. So this is the outcomes, the optimal PMU locations, how the PMU should be placed so as to enrich the system observability, and the wide area monitoring system would be performed. Okay, so this part mainly focused on the wide area monitoring aspect. And again, this wide area monitoring application part, in the wide area monitoring application part, it is for the generation part. What we can consider for the generation part, we have the transmission part and we have the distribution part, right? For the generating part, we can monitor the generation operation status, generator operation status, transient angle stability monitoring. So transient angle stability, because suppose we have the PMUs are giving us the data. So based on the PMU data, if the angles are, means the measurement values are from the PMUs, if we have the changes in the angles, then on the basis of the angle measurements, we can justify whether there is a case for angle stability or the generator operator status monitoring. Okay. So the transmission section, for the transmission part, we can perform the state estimation, load flow, optimal power flow, load forecast, and economic load dispatch part. So mainly for the distributions part, substation automation, feeder automation, consumer side automation, where the substation automation part, mainly it is with the, in suppose in distribution part side, in generally it is considered that daily 5 to 6 topological changes occurs. And based on if there is a mal-operation, then the service restoration needs to be performed accurately. The automatic reclosing, the firstly when there are some faults occurring in the system, so then the reclosing of the system is the breakers would auto reclose, wait for some time, is the mechanism of auto. So this is open, then wait for some time, then close. Then if the fault If the fault is still persistent, then again open, then again wait for some time, and again close, and if the fault still persists, then open. So this is the main operating OTCOTCO. So this can be operating means automatic reclosing operation based on the continuous data monitoring. Then automatic reclosing can be done. Feeder voltages control, active and reactive power control. This can be performed. And advanced metering infrastructure AMI. We have previously discussed the function of AMI, and automatic AMI and AMR, automatic meter reading. So these are mainly the WAMS application. Also, the in the WAMS application, we can monitor the phase angle of the system. Suppose we have one bus and two bus. So if the voltage and angle of this bus is some V1 and del 1, then if we can find out V2 and del 2. V1 del 1, V2 and del 2. So if we have this voltage as voltage magnitude and phase as angle as some del 1, and with respect to del 1 we can find out the magnitude of V2, V1 angle del 1, V2 angle del 2. So this angle change would be giving us the information is based on the bus voltages here. If it can be also done using the PMUs, means optimal PMU placement also, because if we have a PMU here, we have the line parameters known, and then we can directly find out based on the line voltage drops. We can directly find out the bus voltage magnitudes and phase angles in this side. Another part is the also the voltage stability monitoring. Voltage stability monitoring. Uh, voltage stability monitoring, we can also find out whether the knee point means this is the voltage stability curve. So this point exceeds the limit or not. Means suddenly if this part is quite flat, but after crossing this line, the voltage plot means the power versus this is the power voltage versus power. So this voltage suddenly dips, means after this part is quite, means the drop is delta change, means the change of dV with respect to dP is lower. But as we move from this part to from this section, this change is quite fast, and hence the it has to be monitored. Means for voltage stability monitoring, mainly these PMUs would be aiding such contexts or such scenarios. If we have the direct data reporting from these PMUs. So this is the block diagram of the PMUs where of a PMU where the GPS receiver, the global positioning system, global positioning the satellite receiver. Here the GPS system would be means receiving the signals, and based on that, suppose we have a signal, uh, signal is received at some point of time. So phase locked oscillator has to lock the phase lock oscillator has to lock the system in such a manner that the starting of this, suppose this is the reference signal. So based on that, the phase lock oscillator has to log the first pulse, means the sampling has to be performed now. So based on the sampling, when should the sampling start, so that decision has to be made in view of that the both the phases of the means the GPS receiver as well as the phase locked oscillator, they would just the trigger would be at the same point when both the The trigger of this phase lock oscillator would be at the same point when the phase of this GPS signal is locked with the sampling, means the sampling pulse, and hence the NTLS, means the analog inputs, would then only, means when the phase lock has already taken place, then only the analog inputs would be fed into the anti-aliasing filter. So anti-aliasing filter would aid in just sampling the frequencies at a higher rate than the highest frequency that is existing in the in the analog input. So anti-aliasing filter would just allow the sampling rate to be two times the sampling frequency should be two times sampling frequency should be two times the maximum frequency, greater than equal to two times the maximum frequency. So this anti-aliasing filter would aid in just maintaining the, so that the anti so the aliasing effect does not occur. So after that, the 16-bit analog to digital converter, and hence the phasor microprocessor where the programs are stored, and in this phasor microprocessor the phasor estimation takes place, and based on that the output side from the modem, the data is being transferred to the monitoring or the control room. Okay. So in the present scenario of distribution or the smart grid level, so distribution system monitoring with the use of, on one thing is that the PMU is one part, and another is the DFR, digital fault recorder. So this is another, this DFR is another, means it can also, it is a kind of recording device which can record or sample the data at a faster, sample the data at a faster rate than the PMUs to measure the fault. Means during the fault persists for two cycles, and two cycles, within these two cycles, the fault, or in the two cycles, the faults needs to be cleared. So the PMUs, the PMUs can't do that because within the two cycles there might be one data, so, or two data. So what the DFRs does is that the DFR has the sampling rate of from 64 samples per cycle to around 300 56, I think 56 samples per cycle. So these DFRs would be aiding the fault. During the faults they can capture the fault transients on a better fashion than the PMUs. Okay, so mainly it is performed for the pre and post fault analysis part. So, so coming to the distribution system state estimation objective, where the PMUs, or this is a part of wide area monitoring system. So already I have told that the penetrating, or the present day penetrating uh, architecture, even though it's renewable energy, penetrating renewable energy penetration. So based on this renewable energy penetration, the distribution system has become much more. It is a kind of active. It is also known as active distribution networks nowadays. Active distribution networks, and this distribution network, based on the optimal PME placement, would be feeding the data. The network reconfiguration, although in distribution system we have means five topological changes per day, it is general consideration, maybe one, two, three based on the locations, four to five topologies changes per day. So network reconfiguration do occur, and that network topology is a topology monitoring or topology tracking is a major objective of the distribution before the state estimation is performed, which is a part of the WAMS based technique. And here we have the PMUs. These PMUs are placed here. So these PMUs are delivering from the real-time system. The PMUs are placed along with the smart meters as well as the RTUs. So they would be delivering the data to the PDCs, that is the phasor data concentrators. And after that, the phasor data concentrators would be delivering the result to the control centers. And here the state estimation will be performed to find out the bus voltage magnitudes and phase angles. So there are some challenges based on the measurement, number of measurement, placement, and all these things. So for the time being, let's just keep that aside because these are the entire part of state estimation is a is mainly for the smart grid technique, smart grid state estimation, microgrid estimation. All these things do play a vital part in the present day scenario. But for the time being, it can be considered that this is the major operation and that it needs to be performed in the smart grid in the distribution on the distribution side, the distribution level. Okay, so and another thing is that so if we don't follow or don't consider that aliasing effect, anti-aliasing, don't use that anti-aliasing filter. Aliasing effect. So in this aliasing effect, what would it occur means it's generally like this. Suppose we have an AC cycle. So in this AC cycle, if we sample at a faster rate, then we would be getting a discrete form of that AC cycle itself. Discretized form of that AC cycle itself. This would be the discrete data. But if suppose if we do sample the AC cycle, if this AC cycle at a slower rate, so then the reconstruction would lead to some different or rather to a sample of a different frequencies. Means if we have if this can be considered, suppose let us for the time being, this wave or peaks of the wave can't be they can be framed. Means there would be some peaks would be which would be which shouldn't have occurred in this scenario. So or rather if the sampling rate is lower, then the resultant cycle would be of a much lower frequency. Means the resultant cycle of the samples that is obtained would be of much lower frequency. So these are some of the issues. So this to avoid this aliasing, so these anti-aliasing filters are placed in the PMUs. Okay, because if the presence of if some harmonic content is there in the signal, so if the harmonic content is present in the signal but the sampling is not done in a faster rate, so then the harmonics won't get captured and the system would be reconstructed to some different waveform which may represent a sinusoid or something different. So these are the issues and hence anti-aliasing filters do aid in such a scenario. So for that Nyquist rate need to be followed. Hence the frequency of sampling should be greater than twice of frequency of maximum. Okay. So this is the PMU operation. Here is the PMU operation. So here the transmission side, the GPS time receiver side, and based on that DFT means this is the phasor discrete Fourier transform. Discrete Fourier transform is performed as a phasor estimation technique. It is given by Hartke and Thorpe. but presently various kinds of transforms are being performed. Some people have worked on Hilbert-Hwang transform, so you can go through these papers. So this is quite old technique, but this is the conventional one which was initiated by Harke and Thorpe, and hence it is still, as the DFT based techniques are easier to burn in the microprocessor because the microprocessor do have some memory limitations and all these things. So based on the such a scenario, since we need to implement or replicate these devices, or rather these burn these programs that we develop in the microprocessor, so as to in the PMU itself. So the thing is that the PMUs would be delivering some outcomes. PMUs would be delivering some outcomes which should be within that faster time frame. Means if suppose we need to sample in 50 sample 50 samples per second, then within this 50, which is within the when the between this first sampling rate and time and second sampling time, the entire estimation, phasor estimation needs to be performed and output has to be provided. And after that, when the data for the second sample arrives, it needs to estimate the second phasor estimation, and in this process this process continues. Okay, so this is the major PMU operation of the, yes, this is the major PMU operation itself, but the symmetrical component transformation is done for the positive sequence analysis part, and the frequency, rate of change of frequency, positive sequence phasors, real time data output, these are all the outcomes that disturbance and transient detectors. So this is the, now coming to the DFT
Sir,
part. Ah, yes.
how to get previous week classes or notes?
Previous week classes means in these discussion sessions, or the classes means that you can get directly in the portal itself.
These discussion sessions from week 1 to week 3.
Okay, and this week 1 to week 3, this section has also been added in the portal. Means if you log in the portal, then you can get this a problem solving session like this. A new tab has been initiated, and there we would be getting the links of the week 1, 2, 3 discussion, and it would be a Google form is there. You can directly access the link, and uh, you can get access of the previous classes, because uh, we generally upload means, and also the PPTs that we prepare, that also we upload it in the problem solving. A new tab has been included. You just go through the your portal smart grid section, so you will be getting the problem solving session classes.
Sir, NPTEL portal.
Ah, yes, NPTEL portal means that SWAM portal, where you get the assignments and all these things.
Sir, we have to sign in that.
Ah, yes, yes, your personal account that you access for the submitting the assignments, uh, that portal itself. So for that you have some Google account or anything like that what you have created. So you need to just use those means the user account or password, and just log in the NPTEL portal and just access the smart grid course. And there you would be getting a problem solving session tab.
Sir, your voice is breaking.
Voice. So in the problem solving in the portal, just log into the portal, your account itself. You would be getting that problem solving session. Another tab has been added, so you can access this problem solving session. Just click on the problem solving session tab. A Google Sheet will be there. So from there you can access the links and the previous PPTs. Once the PDF.
Okay, sir.
Okay. Okay. So mainly for the DFT part, it is generally full cycle DFT performed, half cycle DFT, cosine DFT, and recursive DFT. So I think in the videos, these are quite clear that full cycle DFT takes into consideration for the cycle of the full cycle, and each and every time it takes the full cycle information. And then suppose the full cycle there are 20 samples, so based on these 20 samples it would be giving out a magnitude and angle result. But this is quite a time taking procedure, and to this is from suppose from 1 to n, means up to n number of samples will be used to, suppose the 20 samples, so entire 20 samples would be used to find out the full cycle DFT, that is the voltage magnitude and the angle. Then for the half cycle DFT, it would be from 0 to n minus 2 minus 1. So here the number of samples gets reduced. So this would be faster in operation. Okay. So here the number of samples,
Sir, what is the full form of DFT?
discrete Fourier transform.
Okay, sir.
Discrete Fourier transform. Discrete Fourier transform. So it is the phasor estimation techniques that I previously have discussed in this slide. This is the phasor estimation technique which is generally performed after getting the data from the PMUs. It means the PMUs would be giving the input to the PMUs at the analog inputs, and which are connected to the CTs or PTs, and based on that the DFT, which it performs the discrete Fourier transform of the signal so as to obtain the voltage magnitude and phase angle, and that's the main objective, means to obtain the voltage magnitude and phase angle. We perform this DFT, and now these are some of the methods of how which DFT is performed and what is the best possible outcome. So here suppose if we have these all these are mainly phasor estimation techniques. Phasor estimation techniques. If we have a full cycle, then suppose if this entire cycle, if we sample it into 20 parts, means 20 samples are taken into the in this full cycle, so then this is called full cycle DFT. Here we need to perform the full, means this, this is the equation, means Vk is equal to 2 by n minus 1, and here it would be n equals to 0. Then Vn e to the power minus j 2 pi n and k divided by n, and this would be from 0 to n less than n minus 1. This is the notation, so you can go through the slides itself. So this is from the slide itself. So this equation, this is the DFT equation for the full cycle. This is the for the full cycle part. If we go for the half cycle, this would be replaced by n by 2 minus 1, because the number of samples would get half. For the cosine DFT part, we will use the, if we have the information of the cosine part, then we can easily use that cosine part to convert it to the sine part. Means if we have the information of the cosine part, suppose let us write Vn cos 2 pi n by n. Okay, so if we have the information of cos part, so if we need to convert this cos to sine, then what we can do is that 90-degree phase shift can be done. So using this 90-degree phase shift, if we consider n minus n pi by 4 part, then we would be getting the sine part. This is the sine part. So what we need is that a real part and an imaginary part. J and imaginary part. Yes, not right. We should not write J here. Real part and imaginary part. So if we know this real and imaginary part, we can directly construct the magnitude at phase angle. So this would give the real part, and sine this 90-degree phase shifted version of this one would give the sine part. So that we from that we can construct the magnitude and phase angle. This is the advantage of cosine. So we need to we are trying to work on the faster DFT approaches so as to, because we have the limitation that if we get a data, if we are sampling at some faster rate, then we need to perform this estimation, phasor estimation within this small window. And if we do perform this, we can deliver the result, then we can develop more accurate or more faster data acquiring devices. So this is the cosine DFT part. So it is generally recursive DFT is used where it is like the full cycle DFT, but we have the information of the full cycle DFT. We just do one thing when we have the recursive use the recursive DFT. If this was our previous window, now we have this as the next window. Now we have the next window as this one. So we just discard one sample from this part. This sample is discarded and this sample is included. So and this entire part remains same, just one addition and subtraction of the sample, and that would be giving us the recursive DFT. This window based sliding window based method, this is a constant sliding window based method, and this results in much higher or much accurate uh, or much faster also, faster DFT or rather phasor estimation. So these are the overview of how the DFT, discrete Fourier transform, works. Mm, then we have the least square based estimation. So in the least square based estimation, mainly we we have some measurements. Suppose we let us consider that we have some measurements, okay, and we have some measurements and we have some estimated value. So what we can what we can do is what we can observe is that suppose this estimated value and this measured value, they are, if they are matching perfectly, then there is measured value is perfect or the estimated value is perfect, okay. So if there are some differences between these measurements and estimated values, then this least square based distribution means, suppose there are differences between and a and b, and if suppose if we if take the difference between a and b, then if both of the values are exact, then it's quite okay. Then if suppose these two values are not same, then what we can do is that if we are targeting to minimize the error, our main aim is to minimize the error. Wait, this least square mainly if we can minimize the error or make the error zero. If the error is zero, then the measurement is perfect. If the error can't be zero, because we need to, we are means ideal case it should be zero, but practical case it has some value. So what we can observe is that if we directly take this subtraction, then this would be, suppose we have 5.2, like 5 is the standard value that should be the outcome. Then we have the, but the measured value is 4.98, then 5.1, then 4.91, and all these things. So if we constantly make the difference of these values, then one would be positive, negative, one would be in positive and negative. Then in such a scenario, a case may arise where if we take the summation of this, if we don't make the least square approach or don't go by the least square approach, then the one case may arise when the sum of these differences might be 0. If sum of A minus B might be 0. Although there are some differences, because since we are using this positive and negative, we are not absoluting this value, or we are just keeping it in the same manner as the values are we are obtaining. So here the error may be, some of these difference may be 0, although there will be some errors. So to alleviate this problem, the least square based estimation is performed, where the differences square of the differences are made, because if we make square, the negative side of the values would also pose or also lead to some kind of values, so which would be positive. So if we can try to minimize this as an objective function, and then the accuracy would be much more improved. So this is the main base of least square estimation. So this is, we need to just find out the a and b, a plus b, t1 will be giving some measurement m1, so a plus b, t2 would be giving m2. So in this manner, the least square estimation, from the least square estimation we need to find out this a and b, and a and b are this is this, it means a and b is the state vector, this vector is the state vector that needs to be estimated. And based on that, if we have have the knowledge of real and imaginary part of the system, then we can, from there we can directly obtain the phasor values, means the phasor estimates, that is the voltage magnitude and the phase angle. So this is the main agenda of the least square based estimation. And also we know that the frequency is a kind is a, we can directly find out the frequency from the frequency estimation from these PMU. So from the frequency estimation here, for a full cycle, one cycle, let's consider this cycle. This is one cycle, and based on this cycle, if these are the zero crossings, these are zero crossings. So based on that, we will get some time value, means this time value, and based on the time value we can find out the frequency, means 1 by time of operation we can find out the frequency. If we get the knowledge of this t1 minus t2, t1 minus t2 would give the time of the, means the time period of this cycle. And this is the phasor rotation based approach, where we can also find the frequency estimation. And last part is the protection aspect, where the protection, why the protection is important for the smart grid architecture, because in the central utility scheme, it was quite unidirectional power flow was maintained, means from top to bottom approach. But presently here the distributed generating resources, due to these energy resources distributed energy resources, the penetration of these distributed energy resources, the protection scheme is becoming more complex, and hence the to give the proper protection, the smart grid protection needs to be established in a better fashion. So for that, the advantages of the relays, means the digital relay, there are some electromagnetic type relays. So what led to the development of digital relays, that means previously relays were kind of electromechanical based, electromechanical electromechanical to static type to digital type. So digital type relays do have the advantage. They do give the advantage of the smarter relaying system, like adaptive relaying, or the auto reclosing options, auto reclosing, adaptive relaying. So these are the advantages, although it has some disadvantages, like the every day the relays are getting evolved. Means the evolution of the relays are quite faster because day and night researchers are working on developing the relays. So the upgradation or the modifications that are getting means incorporated in the present smart grid architecture, that needs to be acknowledged, and that needs to be incorporated in the smart grid trend. So the lifespan of these relays are quite low, and but the operation, the smarter operation for smart grid, we need smarter operation. So smart operation is delivered by these relays. Okay, so these are mainly the advantages and disadvantage. Disadvantage is that regular updation, regular updation. So this is the subsystem of digital relay where we have the first the search filter, so to block the high frequency components. Then we have signal conditioning blocks to allow the signal to flow, means the signal that is required, means the or every each and every information is not required from the operation side. So only that frequency sample, that the frequency component that is required by the system, that is only fed to the relay to operation, means for their operation. And this is analog to digital sample hold, this perform sampling clock. So this is mainly the operation. So we have the ram, rom, eprom, and after that we have serial port where the relays can communicate to other relays. So this aids in communication of these relays, would aid in wider the WAMS based architecture. This would also aid in ones, because in some location if some operation needs to be performed and that information can be shared to that other location, that would aid in the proper functioning of the smart grid architecture. Okay, so and here we have these EPROM. So EPROM is mainly the data repository where we where we keep the basic, the breaker operation, the switching operation, all this information, how what should be performed and on what basis. Then for the ROM, this is the programmable controller where the program or the logic is burned, where for to have the smooth operation, this program is burned in this ROM. The relay, mainly the program logic. Program logic is here, and for the RAM we have the inputs, means the inputs of the signals, inputs of and EPROM is the actions, actions that we need to take. And based on that, the signal conditioning digital output, the contact output would allow the breakers to operate based on the sub, means the digital operation. This is the main block diagram of the digital relay operation. This is the processor. So signal scaling. So we need to perform signal scaling because high voltage, high current side needs to be stepped down to low voltage, low current side. So this is from the lecture slides itself. To the signals are scaled down to for the relay operation. Voltage and current levels are stepped down using the CTs and PTs. So and this is the sampling. So here we can, so if we take the faster sampling rate, means higher sampling rate would lead to proper reconstruction of the signal, proper construction of the signal itself, whereas if we take slower sampling rate, then the signal would be distorted in some fashion. It would be incorporating some harmonic components. And lastly, the relay to there would be, so that relay should follow some features, that is the reliability should be met, and to justify the reliability, dependability and accuracy, these two parameters are being taken into consideration. Dependability and security. So dependability and security, where we can observe is that reliability would be total number of depend the number of correct trips, number of correct correct trips by desired, correct by desired. So number of trips, this is the number of trips for dependability. And security is the correct trips by total trips, total number of trips, total number of trips, total trips. So this is the this reliability of the means the relay should be reliable enough to operate in such a situation where the relay should operate means no such maloperations and all these things should be taken into consideration because if such maloperations would occur then it would be leading to some blackouts and some severe effects in the power system. So relays should operate only when it is required for that testing and validation in hardware in loop validation, software in loop validation. These based on various kind of HIL platform, these relays are tested in hardware scenario. So these are some of the sample questions. So let's do fast. I think it's visible. Hello. You can write in the chat box also. I think options are visible and hello.
So B is the answer B.
B for first one, I guess, right? But tell it. You can use the chat box also to write answer. These are the last year's MCQ questions of the assignments questions. For the first one, it is not B. If you are giving answer for the first one, it's not B. I've just some time ago only I have discussed a digital fault recorder DFR. These are having the faster sampling rates to capture the faults and the transients or transients occurring during the faults post fault situation. So these DFRs have higher sampling rate than the PMUs. So any other no not A faster than PMUs faster than PMUs. This is not A, so it would be D because faster 64 to 356 samples to record the capture the faults. The yes D is the right answer. Correct. So this one last this circuit breaker monitoring data is also formed in yes D is the right answer. Comtrade format. This one which of the following phasor estimation technique can filter exponential decay components inherently.
Option A, sir.
No, exponential filtered exponential DC decay component. This part is the this part is minus which can filter exponential DC component. Only one technique.
Least square estimation technique, sir.
Yes, it's least square. It's least square. So this one GPS each satellite covers dash of the globe percentage or B no not B. It's from the slide itself and from the lecture itself. It's directly from the slide. So uh, there are 24 satellites, and each satellite 24 total satellites, and each satellite covers any guesses? Any guesses? Okay. Okay. So it covers 42. 42 is the right answer. 42%.
How it is 42, sir?
How it is 42? It's a theoretical part, means I can't justify means how it's 42. But out of these 24 satellites, each satellite covered 42% of the entire Earth. Means that's the how
Okay, sir.
42%. Yes. So in WAMS technology, non-operational data is used for mm, this one.
CBM, sir.
CBM, non-operational data. CBM is a correct answer, but some are also there. Means CBM is a correct answer.
All of the above.
Yes, sir. All of them. All of them.
D, sir.
All of them. Achha, this one, I think it is visible. If a signal has fundamental frequency 100 Hz, sampling frequency of 30,000, this one is 100, and this one is 30,000 kilohertz.
300, sir.
Yes. 300. This one, 100 hertz voltage signal is sampled at 5000 hertz. Then the phase angle between two successive DFT is 100 hertz voltage signal sampled at 5000 hertz. Any guesses or otherwise? Uh, okay. So here mainly, if we are to write the the sampling between the phase angle between two successive samples. So for a cycle, the full cycle is 360 degree. Okay. So for this one, 360 into, we can write frequency, sampling frequency by the frequency of operation, and it is two successive phasors. So it is T2 and T1, T2 minus T1. Okay. So what is T2 minus T1? If sampling is done, if sampling is done at this point of time, and the sampling frequency is given as 1 by 5000, sorry, sampling frequency is 5000 hertz, then the sampling T2 minus T1 means the time period between two samples. So this would be giving this T2 minus T1 is 1 by, you can directly write 1 by 5000, and the rest is given. So 360 into sampling frequency is 5000 hertz, frequency of operation is 100, and sampling frequency is 5000 hertz. Frequency of operation mm, by 5000. T2 minus T1, 100 minus 3.6.
So 3.6 in options there is
No, no, it
no
is
3.
mm-hmm. 2 samples. Suppose 700 signal. Frequency of sampling by frequency of operation. So that would be 50 and T2 minus T1 is 5000. So I should put it answer would be 3.6 itself, but I don't have the solution also, but this is the formula. This is the formula, means sampling frequency by frequency of operation into the time of sampling, means between two frequency. Okay, let's the answer would be 3.6 because no other option, but 3.6 is not given, and I don't have the option, means don't have the Answer is given 7.2. But any justification means can you give? Hello, for the 7.2 means this answer. I think Anupam sir has written D. So if you okay, yes, twice of sample. Okay, right. Okay, the answer is 3.6, but at least you need to sample it twice of the sample. So that's the justification. Okay, okay. Thank you. Because the answer is given 7.2. Okay. Yes. Thank you, sir. So yes, it's number of correct trips by total number of trips. Advantage of digital relays.
That's an
All of the above, sir.
Point one. First zero crossing at point zero 0.01. Ninth zero crossing at point zero 0.05. Then the frequency of the signal is for the signal. The first zero crossing is given point zero 0.01. Ninth zero crossing is point zero 0.05. Second, so if we consider the third zero crossing, if we consider the third, this one is the third zero crossing. So if for ninth zero crossing, the entire span for the first two nine is point zero 0.04. So third would be 0.1, 0.2. Fifth would be 0.3. Seventh would be 0.4. Ninth is given 0.5. So what is the frequency of the sample? So each time period comes to means time period is point zero 0.01, point zero 0.01 from 0.1 to 0.2. So each time this part is coming as 0.1. This T is 0.1. So frequency is 1 by 0.1, 100 hertz. This is the right answer. Okay. So okay then these are the parts I wanted to discuss. So thank you for attending this session.
Thank you, sir.
Thank you, sir. Thank you. Thank you so much.
Thank you.